Now, for a cable under a load distribution curve, Wx, and we have this variable load distribution curve, and we can look at a tiny segment of the cable and get this kind of picture right here down in the bottom corner, and look at the sum of the forces in the x direction, which would be t plus delta t times cosine of theta plus delta theta, right there. And then negative t cosine theta. Now we take the limit as the delta theta goes to 0. So this becomes t cosine theta, t d cosine theta d theta, delta theta, which is the derivative of the cosine is negative the sine, delta t cosine theta plus, and a similar term here. So 0 equals all this stuff. We just rearrange. We can get rid of two terms, these two terms right here, and just we're left with the remaining terms. And then we can divide by delta theta and take the limit as everything goes to 0. Now, these two we can right here, these two terms, we could, if you look at dt or dd theta, the derivative with respect to theta of t cosine theta, this is what you're going to get. And here's the delta theta over here. dt d theta delta theta is going to give you delta t, by the way. So you can do by the product rule differentiation, you can verify this. And then as you divide by delta theta and take the limit as theta goes to 0, you're going to find out that this term is not going to matter anyway. So it's only this right here that makes a difference. For f sub y, you get a similar reasoning. So we have, let's see, here's the negative t sine theta right here. T plus delta t sine theta plus delta theta. T sine theta, t, the derivative of the sine delta theta, delta t sine theta, delta t, derivative of the sine delta theta. And then here's the w of x dx right here. And we get it by similar reasoning, we get this. Okay. And this goes back, this just goes back to the previous equations. Did we get, or m naught, did we consider m naught yet? We haven't considered m naught. So that's on the next slide. But remember this diagram. Is this diagram repeated? Yes, I repeated it. So we can get the m's. W delta x, here's k delta x, times the lever arm delta x, minus t sine theta delta x. This would be the t sine theta delta x. And it's about O. It's the moment about O. So then we have t cosine theta delta y, and that's, let's see, W is acting in the positive direction. T cosine theta is acting in clockwise or negative direction, t sine theta in the positive. Now, this is from the previous cell. These two equations right here. This one here and the next one down. and take all of these equations, divide by delta x, and take the limit. So we're going to have this is, and of course, apply the chain rule. So anyway, we wind up with this. So after all this differential math, we get these differential equations. And this is from the moment equation. Yeah. Here's delta y. We're going to divide by delta x. And this will, because you have two deltas in here, and you take the limit as they go to 0, well, you're just going to have 0. So this term won't count in the moment equation, which is right here. Integrating, FH represents the horizontal force. This is the vertical forces, and then we can also make a substitute. Tangent of theta, t sine theta is this, t cosine theta is FH, so we can divide the two to get the tangent of theta and get an expression for y. So this describes the shape of the cable. Now there's this, so this just basically repeats everything we just did. If we have a constant, if W is a constant, then we get this equation, a relatively simple form. Okay, now let's look at an example. So distributed loading is W0. This is a cable stay bridge, and a common way to build them is you have a big fat cable along the top, and the load, as you can see, vertical cables running up and down, and they're constant. The force, the load distribution is going to be constant, that you have a constant load in this section, a constant load in this section, and so forth. These vertical cables are holding up the bridge deck, and this big fat horizontal cable at the top is being pulled on by a constant W0 as a function of x, as a function of this distance. We're ignoring the cable's own weight. Later we will not ignore the cable's own weight. So we get this, we get an expression for doing the two integrations. We get this, we get C1 and C2, they're constants of integration. At the boundaries, let's go back. At 0, dy dx equals 0. At L over 2, y is equal to h. So let's take a look at that. At x equals 0, y equals 0, that forces C2 to be 0. The derivative at 0, the derivative equaling 0 at x equals 0, well, we get that that would force C1 to equal 0. So we just get a simple parabola right here. Then we look at the boundary conditions. At y equals h at L over 2. So we can go up here. When we substitute L over 2 for x, then y is equal to little h, the height of the cable. Let's see. Let's go back. Just look at the picture again. When x equals L over 2, y equals h. So that allows us to get f sub h. And then we can do all these substitutions and we get our final answer. We want to know when the tension is maximized. So let's go back. Now that we know f sub h, we can get f sub h. Let's go back and find out when the tension is maximized. Well, now that we know f sub h, the tension is going to be maximum when theta is big. f sub h divided by cosine of theta, and theta is this angle right here. F sub h divided by that cosine is going to be equal to the tension. And the tension T is not a constant magnitude because we have forces. The forces are not perpendicular to the cable. Unlike a pulley, the forces are perpendicular to the cable going over a pulley, so the magnitude of the tension doesn't change on a pulley. The magnitude of the tension will change in this situation because we have forces that are horizontal. We have load forces that are horizontal to the cable. So the tension is going to change in this case. We'll find that's also true of friction, by the way, when we get to that section. So FH over cosine theta gives you the tension at whatever angle there is. When theta is big, cosine theta is small, which will magnify, which will make T bigger. So we want to find the maximum theta, which is at the beginning or the end. So whenever, there it is right there, the maximum tension is at your maximum angle. Maximum tension occurs at the maximum angle. And we can get that tangent from this equation here. Okay. And then we can also get the value of T max. So the cosine of theta is expressed, well, here's the, you can get the tangent of theta is all this stuff and work it out. You know, T max, what does the cosine of theta have to be? And it's trigonometry from then on to get to this point. Okay. Total length of the cable. That would, now the cable dips down and comes back up. So you got to integrate this. And you can integrate it with respect to dx. This is tangent of theta. We already know the tangent of theta. Where's the tangent of theta? There it is. Right there. W naught L. Where's W naught L? Come on. There we go. Dy dx. Oh, yeah, there's an x here. There we go. Oh, my mouse is flipping around the cells. So taking the derivative of y with respect to x gives you this value, which would also equal the tangent of theta. And then you can find out the total length. Inverse, this is the inverse hyperbolic sine. We're going to get, we'll see it in another place also. So we'll talk about it a little later. And we'll end the video here. We'll talk about cables under their own weight next.